So the norm of a vector is square root of 2 squared, which is 4, plus negative 4 squared is 16, plus 5 squared is 25. And so that's going to be the square root of 45, right? So, and then if we have the norm of a vector quantity squared, it's going to be 45, right? And then times a vector, which is, I can either write it in vector notation, or what I might do is write it as 2i minus 4j plus 5k. And so certainly this is a correct answer, but I could also go ahead and multiply this scalar times each component, and then that would be minus 16/45 I vector plus 32/45 j vector, j hat, I hat, j hat, sorry, and then 5 and 45 cancel to 9, so minus 8/9 k hat. And of course, as vector notation, we could write that as minus 16/45, 32/45, and minus 8/9. So that would be the vector projection of B vector onto A vector. So I'll let you do the other one, the vector projection of A vector onto B vector. But, to me, this formula would be a little bit easier to use here. Otherwise, you gotta figure out what that angle theta is, which we can do that as well. So maybe instead of doing the other vector projection, because you don't have an answer to that, why don't you go ahead and use the other formula for this? Use the one where it would be norm of B vector cosine theta, which you have to figure out what cosine theta is, and then times the A vector. I think that was the other formula that we had. So, but we'll go from there. So now I'm going to move on into something else, and we're going to look at force and work and distance. So we'll look at that a little bit. So trying to verify before I move on. Yeah. So anyway, that was the formula. So let's go over to force. So we kind of glazed through chapter 6 and some of the applications, but in section 6.4, so you can use that as a reference, go back and look at that. We had that work done was force times distance. And of course, that was assuming that if we had a force, if we were pushing something along a certain distance, taking this box and pushing it in the same direction, that was just an easy application. And so if force is in pounds, a lot of times we'll measure that in pounds, and the distance is in feet, then the work is going to be what we call foot-pounds, which is really feet times pounds. But anyway, because it's multiplication over here. So what happens is that's when we're having that force in the same direction. But that doesn't always have to be the case. What happens if we have a force kind of pushing up on this, but or maybe better visual would be a force pushing down on this at an angle. And if this is ice right here, and that ice is going to slide on a floor, this is more real life. And I know you want me to draw a smaller box over here, but let's call it dry ice. That doesn't melt. Probably didn't slide very good either. But anyway, we got some force here, and we're pushing this this way along the floor. The question is what happens there? And we're going to end up getting a result that's very nice and very similar to a linear work done. But basically, we have a displacement vector that we're going to have. So that's the distance that we go is the displacement vector. That was actually blue before, right? And then we have a force with an angle in between, right? So there's going to be an angle theta in between these two things as well. And so really what we have is we're going to want the scalar projection here. We're going to want the scalar projection of F onto D, where, you know, D was the displacement vector. We'll call that D vector. Okay, and like I said, that should have been blue because that was actually, this was a blue vector here. But anyway, so what we're going to want to do is we're going to want to look at the scalar projection of F vector onto D vector, and then times this displacement vector. Okay, so really we want the vector projection here, and if we do that, the vector projection, let's see, is the scalar. Well, we're going to want the scalar projection. So the work done is going to be the scalar projection, which in this case will be the norm of F vector times cosine theta times the norm or the size of the displacement. So the distance would be the size of the displacement vector. So that'd be the norm of the displacement vector. Okay. Now we can, if this is going from point A to point B, then we can call the displacement vector, you know, vector AB. So that's kind of what they do here. So instead of this, they're going to say, hey, norm of F vector cosine theta, which once again, that's a number. That's the scalar projection, right, of F vector onto the displacement vector. But anyway, they put, you know, kind of norm of AB here, or the distance there. Now, what it actually ends up being, if we rearrange this, I'm going to stick with this one. If we rearrange this and rewrite that as norm of F vector times the norm of D vector, because these are all numbers, right, times cosine theta. Well, if you notice by our theorem, cosine theta is equal to F vector dot D vector divided by the norm of F vector times the norm of D vector. So this is equivalent to what? Just simply F vector dot D vector, and that would be the work vector. I'm sorry, this is a vector, isn't it? The work vector. No, it's not. Dot product is a number. So they have a capital bold W in the book for their example, but the work is not a vector, it's a number. So in example 6 on page 857, that should not be W vector, it should just be a W. But anyway, so what did we have before? We had W equals F times D, force times distance. So now what do we have? In this chapter, we have W, if the force is coming in at an angle, it's going to be the force vector dot the distance vector, or the displacement vector, basically the distance. So this is, it looks very similar if you write it like I did, and but now it's a dot product. So very nice result here. So let's look at an example of this. Hopefully I'm not running out of time, but let's do number 37 in class here. So let's do number 37. So page 859. Force F represents a force with a magnitude of 8 pounds. So how do I write that? Well, the magnitude of the force is 8 pounds. So that's the norm of F vector. And the theta angle that is going to be applied is pi over 3 radians. Okay. So find the work done by the force in moving an object along the x-axis from the origin. So we're starting at the origin, and we're going to go out to 6 units to the right along the x-axis. Okay, and then I'm going to have a force or an angle of pi over 3 units. Okay, so I've got force pushing on this. So really, you know, I'm gonna draw it like that force vector, and this angle here is pi over 3. Okay, so anyway, so that's, and we're pushing from 0 to 6 along the x-axis. So what would this ordered pair would be over 6 up 0, right? So the displacement vector, basically what can we do? We can just subtract the components of the ordered pair. So the displacement vector is going to be, you know, 6 minus 0, which is 6, and then 0 minus 0, which is 0. So the displacement vector is 6, 0. So we have that. And we have the norm of the force, and we have the theta here, right? So the question is, how do we use that data to come up with the work? With the work is the force vector, which we don't have, times the displacement vector, which we do have. So doing that, the force vector, coming up with that, is going to be the size of the force vector times, if you remember what's the components of the vector, it'd be cosine theta I plus sine theta j. So that was back from section 1, I believe. So anyway, what's this? This is going to be 8 times cosine of pi over 3 I hat plus sine pi over 3 j hat. Okay, sine of pi over 6 is a half, so cosine of pi over 3 is a half. So this is 8 times 1/2 I plus square root of 3 over 2 would be the sine of pi over 3 j hat, and then multiplying through by 8, we get 4I hat plus 4 root 3 j hat. So that's F vector. So I have that, which I could rewrite that as 4 and then 4 root 3 in vector brackets, vector notation, right? So anyway, and so force vector dot distance vector is 4 and then 4 root 3 vector dot 6, 0. And if I do that, that'd be 24 plus 0, which equals 24. And what would the label be? Foot-pounds, right? So foot-pounds. 24 foot-pounds for part A there. And then I believe it also says, well, what happens if you do it vertically along the y-axis from the origin to 0, 6, and of course that would be very similar, but instead of going the displacement vector there, I'd be going up to 0, 6. So this vector, this distance vector would be, instead of 6, 0, it'd be the displacement vector here. I meant to use a different color. But this displacement vector here up to 0, 6 would be, so this distance would be, distance vector would be 0, 6 vector. Okay, so basically the only thing that changes, this would be 0, 6, and then what do we get? So when you dot product this, we're going to have the same force vector, but anyway, it'd be 24 root 3. So the work done vertically would be 24 root 3 foot-pounds. Okay, so that's the number 37 there for you, so that should help out. And then last but not least is if I only got about a minute left, so I'm going to have to reset this. So I'm going to do one more example for number 55, but I have to reset my time.